three asymptotic notations last time. The first one, little o. When we compare a concept called order of growth, the order of growth of f function less than the order of growth of g function, then we use this little o notation. F of m belongs to little of g of m. Then another two asymptotic notation, capital theta, big theta, all right, big theta. There is a little theta, but it's rarely used. So here, in this class, we will not talk about little theta. So big theta, but we use big theta. So big theta, these two functions have the same order of growth. The third one, the order of growth of f function is greater than order of growth of g function. So that's the little omega. So these three. And in order to tell if, so which of these three asymptotic notations should be used when we consider two growth functions, we calculate the limit. We use the limit. If the limit equals 0 or limit equals non-zero, positive constant, or the limit equals infinity. So these three cases. So that's what we learned the last time. All right. Before we move to the next topic, first, I need to clarify one important concept here, this order of growth. Because I didn't give you the definition of order of growth. Last class, I didn't give you. What's the order of growth? So we imagine there is a abstract concept, order of growth. Here, I like to give you a concrete. So it's not definition, it's a concrete way to describe order of growth. All right, so what's that? First, let's consider simple function. Then we look at the order of growth. Simple function, power function. Power function. The order of growth of the power function is very easy. We can use a concrete number to represent the order of growth for the power function. So what's the power of function? Variable is n, power, exponent is a constant. Here we use constant number d. Constant number d, order of growth. D greater than 0. Okay, it's a positive constant number. N to the d, so this is a power function. Okay, so for this power function, we can define order of growth easily. Order of growth is this d. The exponent number is the order of growth. All right, so this is the easiest way, so you can get a specific number for the order of growth. But we know power function is just a special function. There are many functions different from power function, right? Different from power function. All right. So when a function is very complicated, and many times you cannot use power function to represent, right? Yeah, many times it's hard to represent using the power function. Okay, yeah, all right. So then you may ask, if a function is not a power function, how can we get an order of growth of that function? That question, okay, yeah. Sometimes, yeah, not very easy to answer. Yeah. Here, let me try to answer that. So for a non-power function, how to see its order of growth? First, let's consider the log function. Log function. Yeah. So we know the log function, we frequently use the log function. Yeah. LOGN. What is the order of growth of log function here? This question, log function, what's the order of growth of log function? Yeah. Because this function is so important. Yeah. So if you want to answer this question, then it's not that easy. Yeah. Yeah. Because for the log function, if you compare it with a power function, then how do you compare log function with a power function? Log function with power function, okay? So here, there is a question we need to answer. Question. So what's the question? Compare the log function with a power function. Later, we will do that. When we move to the examples part, so today we will do a lot of examples. After I talk about the definitions, then we will move to the examples. So we will answer this question, compare log function and the power function. Yeah, all right. So then, in order to describe the order of growth of log function, we may need to use a very abstract way that we used in your calculus. In your calculus, now, do you remember in your calculus you learned a special language to describe the definition of limit and a derivative? There is a special way we do the definition using epsilon delta language. Epsilon delta notation language. Any of you? Yeah, very abstract. Yeah, in calculus, the definition is very abstract. So here I do not do this. Okay, I will not go there. Yeah, but there is one little idea from epsilon delta language we may borrow here to describe order of growth of log function. So what's that? Log function, you can connect to a special power function, and to the epsilon. The exponent number is epsilon. But what's the epsilon? Here, let's use our calculus understanding of epsilon. What's the epsilon in calculus? Okay. So it's a number. Oh, yeah. It's a number. You can use this. First, it's a positive number, right? Epsilon must be positive. Then it is less than any positive constant, right? We can make it smaller than any positive constant. Okay? Given any positive constant d, we can make our epsilon less than that. That's in calculus, we use epsilon in this way. So special. Yeah. Epsilon in calculus. Here, if you really want to connect log function with a power function, it should be n to the epsilon. That epsilon is first positive number. Second, it is smaller than any particular positive number. No matter what d is, if this d is 0.0001001, this epsilon still less than that. That's the epsilon. Okay? So we borrowed that abstract way, a very special property, abstract, that's the epsilon. This is for imaginary understanding. This is not a rigorous definition. This is not a rigorous definition. This is a special way to understand this order of growth concept for log function. Log function too, so special. Now, later, when we compare log and n to the d, so you will see. Then you connect this description. You can get a better understanding. Yeah. All right. Yeah. So next, let's move to C.2, definition of asymptotic notation. Yeah. Yeah. Another important thing. Yeah. Before we move to that definition, using upper bound and lower bound. Yeah. Remember in the previous slide. So let's move to the previous slide. There is case number 2. There is case number 2. We could use the limit way to look at the case number 4. Sorry, case number 4. We cannot use the limit way because the limit does not exist. So the question is, how do we study case number 4 if the limit does not exist? Then we use another special way. We avoid limit. Because limit does not work. So we do not calculate the limit. So what do? We use inequalities. We don't do a limit, but we use inequalities to get upper bounds, lower bounds of a function. That way, we compare two growth functions. We use the inequality way to compare order of growth. Yeah. All right, objective. The limit does not exist, okay? But we still want to compare two growth functions. Yeah. So now, the inequality way. The function g of n is usually a simple function. Simple, usually we use power function, and or a power function multiply log function. So that's the most commonly used growth functions in algorithms. Either power function or power function multiply log function. Most commonly used growth functions for this class. All right. The function f of n could be a complex function. Yeah. If it's a complex function, then here we try to use constant multiple of g function to approximate f function. That's the way, approximation way. Yeah. But how do we approximate from two sides? Lower bound, upper bound, we try to approximate this function from two sides. In this way, we can compare these two functions. Yeah. All right, so use the constant multiples of g function to approximate f function. Yeah. Specifically, we want to find two constants, positive constants, C1, C2, positive constants. One for lower bound, one for upper bound, such that this inequality, okay? This inequality, we approximate f function from the lower bound, C2 multiple of g function, C2 multiple. Upper bound, C1 multiple of g function. Approximate from the upper bound and from lower bound. Yeah. in this way, if we can find C1, positive C1, C2, and get this inequality between f and the g functions, then our conclusion is these two functions have the same order of growth. Okay? Here, you do not see the limit, but our conclusion is these two functions have the same order of growth. Yeah. All right? Yeah. So the conclusion, f g have the same order of growth. Okay? Yeah. Yeah. See? Yeah. Yeah. All right. And if we use the asymptotic notation, here we can use asymptotic notation from the previous slide. We can write f function belongs to cap big theta of g function. Same order of growth in this way. Okay? Yeah. So here you can see, yeah. So let me summarize a little bit. Yeah. We learned 3 asymptotic notations so far. Little o, cap big theta, little omega. But for little o and little omega, we have to use limits to determine. Yeah. So these two cases, we have to calculate the limits to see if f should be in little of or little omega of g function. But for big theta, we have 2 ways. Big theta, 2 ways. The first way, limit way. The second, inequality way. Okay? 2 different ways to determine if 2 functions have the same order of growth. The summary, that's all right. Then let's move to the next topic. The rigorous definition of 3 asymptotic notations. 3. Yeah. Among the 3, 2 new asymptotic notation. The third one, big theta, old one, yeah, we learned, but we will use this way to describe. Yeah, this way to describe. Yeah. Because the previous way is the limit way. Yeah. Oh, the previous way is the limit way. Yeah. So here, another point I want to mention here. Yeah. That is the limit. It's possible when we calculate the limit does not exist. The limit does not exist. But these 2 functions have the same order of growth. That's possible. The limit does not exist, but the 2 functions, they have the same order of growth. Let me give you this example, this interesting example. Okay, all right, yeah. So this example, limit does not exist. Okay, yeah. So let's calculate these 2 functions. The first function, and 2 plus this function, okay? 2 plus parenthesis -1 raised to nth power. Yeah. So you know, when n is even, it's 3, right, in the parenthesis. When n is odd, it's 1. So 1, 3, 1, 3. These 2 numbers change alternatively, right? Yeah, that way. Okay, that way. Yeah. Alternate the pattern like that. Okay, all right. So the lower function, let's use this one. N squared plus 1, 3 minus -1 to the nth. How about that? N squared plus 1. Okay? Then big parenthesis, 3 minus parenthesis -1 to the nth power. Yeah. All right? So even, odd. Okay? Yeah? All right. So, all right, yeah, so square, okay? I put a square, because I want to show the limit does not exist, but these two functions have the same order of growth, okay? These two functions have the same order of growth. Okay, all right, yeah. First, can you see limit does not exist? Can you see the limit does not exist? Okay, because for this part, close to 1, right? That part, n squared over n squared plus 1, when n goes to infinity, approaches to 1. Okay, so it's gone. Okay, then let's look at the, parenthesis part. In the parenthesis part, even, odd, take certain pattern. Let's look at the pattern. So what's the pattern? The pattern is when n is even, 3 over 2, right? When n is odd, 1/4. So take this pattern. Forever. Okay? Does this sequence has limit? No. It does not converge, right? Up or down. It never converges. This sequence must approach to one number. But this one does not approach to one number. Okay? So there is no limit in this case. No limit, but we will, if we use inequality way, we will use this inequality way, we can see these two functions, they have the same order of growth. We can find a C1, C2, when we compare these two functions, upper bound, lower bound. You can see, even the limit does not exist. We can use the inequality way to get a conclusion. These two functions have the same order of growth. Okay? Yeah. So this special example. Yeah. Because I may create a concept question. I use this example as the background. I can create a concept question. Ask you, suppose the limit of these two functions does not exist. Is it possible to show that these two functions have the same order of growth? No. I can make a question like this, right? Yeah. So you need to know this example, then you can answer this question. Otherwise, you may not be able to answer the question. If you do not know this special example, how can you see it? Right? Okay, all right, so let's move to the next topic. C.2. Define asymptotic notations. Rigorous but abstract definition. All right, first, we define big O notation. Another asymptotic notation. This one is the big O, little big O. See? We define the little O. Here, the big O. Okay, all right. So what's the definition? For a given function g of n, the notation big O of g of n represents the set of functions f of n that satisfy the following condition. So what's the condition? There exists some positive constant c and some non-negative integer n0 such that this inequality holds. What inequality? F of n less than or equal to c times g of n. Here you can see this big O notation, we only look at the upper bound of f function. We use a constant multiple of g function to approximate this function from the upper bound side. We do not look at the lower bound, upper bound. So if you have this condition, then you can say f of n belongs to, here, make sure for all n greater or equal to n0. There is a special number, n0. Later I will explain the role of this n0. It's important. Special role of this n0 and not. Okay, all right. So then, so this gives us the big O notation. So all such functions satisfy this inequality. We say they are in this big O of g of n. Set. It's a set of functions. We define this notation as a set of functions. And here, let's look at this n0. It's a row. This n0 is so special. First, it must be a constant. This n0 must be a constant. That is, you have to fix it. But it's a special constant. You have freedom to select this constant. You have freedom. You can determine this constant based on the given functions. But after you determine that constant, you need to fix it. When n changes, when this variable changes, you cannot change this n0. Okay, you have to fix that n0 constant when n changes. But at the beginning, you have freedom to select any number as this n0 constant. So that's the special property of this n0. All right. So then, sometimes people do not need to say this n0 notation explicitly. So sometimes, especially in calculus, because this notation we borrow from calculus. So in calculus, people use the language like this, when n is sufficiently large. In this way, we do not say n0, right, explicitly. Okay? So from the description, you cannot see n0. But we use some, vague way to mention that n0. So when n is sufficiently large, what do you mean n sufficiently large? Okay, so there is some hidden n0 there, hidden n0. So if you can find this special n0, and when little n is greater than that n0, then the inequality holds. That's what we mean when n is sufficiently large. Okay? All right. So that's the first definition. If we use a graph way to see the relationship between these two functions, you can see here we can use c constant multiple of g function. After we multiply appropriate positive constant c to that g function, then we can adjust Because when we change the value of little c, we can change the graph of c times g of n up or down, right? Raise up or down, okay? Yeah. When we raise to somewhere, it completely cover the graph of f function. That's the visual understanding. Completely cover, okay? But complete cover, there is a special part we need to, after the vertical line at n0. Before this vertical line, we don't look at it, okay? Yeah. Before that vertical line, the c constant multiple of g covers f function or not, it doesn't matter. So here you see, doesn't matter. Cover it or not, it's not important. Okay? Only after that vertical line, it's important. C times g function must completely cover f function. That's the meaning. Okay? Yeah. So here, why this part not important? Before certain vertical line, the n0 line, it's not important. That means when the problem size is relatively small, so this part relatively small, right? Yeah, this part. When the problems are relatively small, remember, yeah, the performance of these algorithms could be distorted by overhead. Remember, there is overhead concept. So what's the overhead concept? To run an algorithm, you need to do a lot of preparation, right? You need to set up. You need to prepare, okay? You need to do a lot of preparation work. So that work, we put it under the part, overhead part. Yeah. So when the problems are relatively small, if you compare the efficiencies between different algorithms, the efficiency numbers could be distorted by the overhead. Okay? It's not reliable. Not reliable. Distorted by the overhead part. Then we should not look at that part. Okay? We should not look at that part. Okay? So we move the vertical bar. Okay? Yeah? Somewhere, appropriate location, such that we can bypass the overhead part. Okay? Bypass the overhead part. So after that, then when we look at the problem size goes bigger and bigger, then we compare the efficiency numbers, then it's important. It's important. No. Okay? Yeah. So that's the meaning. That's the way to understand the asymptotic notation. Yeah. All right? So this is the first one. After the first one, then the second and the third, we just do the similar way here. Okay? We do small adjustment. So similar way, small adjustment. Okay? Using the similar understanding. But only we added lower bound. Here we only talk about upper bound. We can add a lower bound the same way. Yeah? So we get two more definitions of asymptotic notations. The next one, big omega notation, lower bound. This is the lower bound version, big omega. Okay, all right, definition. Yeah. So this time we use a different big omega of g of n to represent another set of function. But this set of function we do approximation from the lower bound. Yeah. Still, we use some positive constant c and n0 number, yeah, passing some vertical line, yeah, passing that overhead part, okay, yeah, yeah. But we approximate f function from the lower bound, okay, yeah, below, yeah. F of n this time should be greater or equal to C times G function. All right, yeah. So that's the big omega notation. Yeah. The graph, yeah. So this time we use C times G function, but we need to approximate F function from below to support F. Okay, yeah. From below we do not call upper side cover, below support. Okay, support that F function. Yeah. Completely support F function. Okay, from below, yeah. And vertical line, so this part doesn't matter, you know, yeah. Same understanding as before, okay? Yeah. So this is the big omega notation. Then next one, combine two-sided approximation, both sides. This is the big theta notation. All right, so this time big theta and two positive constants, C1, C2, and non-negative and zero, vertical line somewhere. You can make your decision. Okay, you have freedom to move that bar. Okay, yeah. But after you find appropriate n0, you should fix it. Okay, do not change it. Do not change it when the n value changes. When the n value changes. Okay, yeah. All right. So you get this up inequality. Yeah. C2. Yeah. C2 G of n less than or equal to F of n less than or equal to C1 G of n. Yeah. All right. The graph, this time you use C1 multiple of G and C2 multiple of G. You approximate F from upper side and the lower side, both sides. Okay? Yeah. Then our conclusion, these two functions have the same order of growth, and we use this capital big theta notation to represent. Yeah. Okay? Yeah. All right. So that's the definition. Yeah. The rigorous definition of these three asymptotic notations. Yeah. So pretty abstract. Yeah. I hope you can understand. Yeah. All right. So next. Yeah. So before we move next, any question? So you want to ask? Yeah. All right. Yeah. Yeah. Try to understand. Yeah. Yeah. Pretty abstract. Yeah. Next, let's do several examples. C.3. Yeah. So to improve our understanding of the asymptotic notations. Also, we need to derive a few important results. So in our homework questions, I will give you a few questions using the results we derived here. Okay, yeah. Yeah. All right, so let's look at the question. The first one, yeah. Show f function here. F function is simple n plus 2 function. N plus 2 function belongs to big theta of n. How to show it? Okay, so very simple. Yeah. Here, when you look at the big theta, in order to show f function belongs to big theta of g function, I mentioned two methods, right? So you can use two methods to answer this question. The first method, the limit way. So you want to see if the limit exists and it's a positive constant. Then you can show the conclusion here. Okay, all right. So here the limit is very easy to calculate. So what's the limit? Limit when n goes to infinity, n plus 2 over n. Can you see the limit equals 1? In calculus, if you use the calculus way, can you see n equals 1? Yeah. So usually people do this way. Yeah. People write, if you feel hard, so people write another way, so you can see a little better. Limit, you do division, numerator, denominator by n. Okay, numerator divided by n, you get a 1 plus 2 over n. Yeah. Denominator, you get a 1. Okay, but 2 over n, when n goes to infinity, goes to 0. Right? Yeah. So then you get a 1. Okay. Yeah. One more step, so you can see better. The limit is 1. 1 is non-zero constant. So based on our method 1, the limit is a non-zero constant, positive constant here, positive constant. Yeah. Your conclusion is big theta. F belongs to big theta of G. Yeah. All right. So that's the limit way. Yeah. Next, I want to use the definition way. Use the inequality way. So we do the same thing, but we use the upper bound, lower bound. Yeah. All right. How to get upper bound? So when we start, yeah, we need to find the C1, C2. And the C1, C2 multiples of G function, one we use as the lower bound, another use as the upper bound. All right. So let's do this way. Let's look at lower bound. Lower bound easy, right? Lower bound easy, yeah, because n plus 2 greater than n. N is a constant multiple of g function, because g is n. G function is n. Okay. Yeah. So here you can see, yeah, this inequality holds when n greater or equal to 0. Because in this class, our n always greater or equal to 0. We do not consider n negative, right? N is our problem size. The problem size can never be negative number. Okay? So n is greater or equal to 0, this inequality holds. Yeah. If in math, n is a negative number, even n negative number, this inequality also holds. Yeah. But in our context, we do not have negative value for n. So for that reason, we use this n greater or equal to 0. Yeah. All right. So that's the C2. So we find the C2 equals 1. Okay. Yeah. How to find the C1? Yeah. How to find the C1? Yeah. Here, because n plus 2. N plus 2 less than a constant multiple of n. C1 times n. So here we need to do a little more work. Because we need to change this 2 constant term to a constant multiple of n term. Constant multiple of n term. So what's that? We want to replace 2 by n. 2 by n. And make it larger. We want to replace 2 by n and make the result function larger. That means n should be greater or equal to 2. N cannot be less than 2. Okay? N should be greater or equal to 2. So this is our condition for n0. Remember, we need to determine that vertical bar, that n0. So this, the range here, give us that n0 number. Okay, yeah. So we need to put it here. Yeah. N greater or equal to 2, this condition. Then we have this upper bound. N plus 2 less than or equal to 2 times n. We get upper bound. Yeah. So the C1 equals 2. So we find the C1, C2, then n0. N0 should make these two ranges both true, both, so n should fall into these two intervals. So we select the second one. Okay? Because if the second one holds, the first one must hold, right? If the second one holds, the first one must hold. Okay? So then we take the second one. Okay? So that means n0 equals 2. So if we use the definition way, you need to find these three constants, C1, C2, and n0. So then you use the definition way to answer this question. Okay, all right. So that's the first example. How to apply the definition to answer this question. Okay, yeah. All right. Second example. Now we need to show n cubed belongs to big omega of n squared. Lower bound. Okay. When we talk about big omega, we do not look at the upper bound. We only look at the lower bound. How to get a C function, a C constant, such that n cubed greater or equal to C times n squared, right? Yeah. Yeah. So because our goal, we want to see n cubed greater or equal to n squared. Yeah. Here it's easy, you can see, yeah, because n only takes discrete numbers, right? But n takes discrete, non-negative discrete, and when n greater or equal to 0, this inequality always holds, right? Yeah. N equals 0, both sides 0. N equals 1, both sides 1. After that, n cubed strictly greater than n squared. Because you multiply one more n. N is greater than 1, so it can only be larger. Yeah. So this question is very easy. Yeah. C equals 1. n0 equals 0, yeah. So the definition applies. You can see, yeah. So we get a conclusion here. Here you cannot use limit. This case, there is no limit way, okay? So only the inequality way. Yeah. So this is the second example. Yeah. All right. Third example. We modify our first example slightly. Yeah. So this time we raise n plus 2 to third power. Third power. Yeah. Can you still find two constants C1, C2 for lower bound and upper bound? Right? Can you still find that? Yeah. Yeah. Here, a little harder than our first example, yeah, but not too much harder. Yeah. Yeah. Although here you can still use the limit way, right? Yeah. Here the limit way still works. Yeah. So you calculate n plus 2 cube over n cube. Okay. Yeah. So one way is you put the cube outside. N plus 2 over n. And we know inside the parenthesis, the limit equals 1, right? So 1 cube, it's 1. So limit way, very simple. Yeah. But here I want to show you the definition way. Inequality way. Let's look at the lower bound first. Easier, lower bound. Okay, yeah. And we know n plus 2, positive number, right? Yeah, positive number. Okay, so n plus 2 greater than n, n plus 2 is a positive number. n is a non-negative number. Yeah. So they cannot be negative. If they cannot be negative, then we can raise to the same power, right? Yeah. Same power. Yeah. Cube. Yeah. Still true. Yeah. So when n greater or equal to 0, this inequality holds. And we get C2 equals 1. Yeah. Next, upper bound. Upper bound. Yeah. We need to find the C1 constant times n cubed, upper bound greater or equal to the f function. F function. So for the upper bound, we do this way. We do this way. First, we find the upper bound for the function inside the parenthesis. We do not look at the exponent number. Yeah. Only look at the base part. Yeah. N plus n. Yeah. So n plus 2 less than or equal to n plus n. That is 2n under the condition n greater or equal to 2. Yeah. So you have to put this condition, otherwise it may not be true. Yeah. So you have to specify the right range here. All right? Yeah. Then we have the inequality n plus 2 less than or equal to 2n. Then we raise both sides to cube. Yeah. Both sides cube. Yeah. The cube of 2n, 8 times n cubed. 8 times n cubed. So you get that constant 8. So C1 is 8. C1 is 8. Yeah. Yeah. So here, although this method is so simple, yeah, but I want to point out one way that many students, so they did in the wrong way before. Yeah. Yeah. So I assigned similar question long time ago. So many students did way. Many students, they expand this cube, expand it. Okay, so they apply the formula a plus b parenthesis cube. They apply that formula. Oh, Pascal's triangle, remember? Yeah. Binomial formula, Pascal's triangle. Yeah. So that, yeah, those students, they know that formula. Oh, they can find that formula. Okay, n cubed plus 2 squared 3 times n squared 2n 6 n squared plus 3 times n 2 squared 2n squared 12 n and plus 8. So they expand this n plus 2 parenthesis cube to this polynomial. Then, from this polynomial, if you want to find less than or equal to some C1 constant n cubed, then it's not that easy, right? Yeah. So then those students, use very complicated way to get that C1. Because this expansion way is not the right way. Okay? Expansion way, you make things harder. Don't do expansion. Okay? So we do inequality here directly. Then we raise to cube power. Cube. Yeah. Then much easier. Yeah. Otherwise, if you do expansion, very complicated. Yeah. Because I remember the question I gave to those students, not a cube, the question I give them to the 5th power. If you do expansion, then even more complicated, much harder. You don't need to do the expansion. So 5th power, you can still use this way, right? Yeah. Much easier. Okay? Yeah. So that's the right way to do it. All right. Example 2.4. Yeah. Show that log of n belongs to little o of n. This time we compare log function with n function. N function is a special power function, exponent number 1. And here it's a little o. So for this, to show the little o, we can only use the limit way. We calculate the limit of the ratio of these two functions. But remember, when we calculate the limit, if you want to apply the L'Hopital's rule, you need to convert it from discrete variable to continuous variable. I mentioned last time. Otherwise, you cannot take derivative. Okay? Remember that continuous variable, discrete variable. Okay? All right. Yeah. So let's calculate the limit, but this time for the continuous variable. Log of x over x. This log here, we assume use the log of base a greater than 1. Yeah. Hidden, we use a hidden base, a greater than 1. Yeah. Okay. Yeah. Then this is a indeterminate form, right? Infinity over infinity indeterminate form. So we can apply a L'Hopital's rule. Now, so here, let me write. You need to do the checking, okay? Check infinity over infinity indeterminate form. Okay. Now, then take derivative. Denominator derivative 1. X derivative of x, it's 1. Okay. The numerator, so you can find the formula. Okay. You can search, find the formula. Yeah. So 1 over constant natural log of a, that constant. It's a positive constant. We know this constant is positive because a greater than 1, positive constant number, times this x. Okay, then we simplify the fraction. After simplification, this form, it's not indeterminate. The numerator is 1. Then it's not an indeterminate form. You cannot apply L'Hopital's rule another time. Okay, don't do it. You cannot apply L'Hopital's rule another time. Here you need to calculate the limit directly. Calculate the limit directly. Numerator 1, denominator x goes to infinity, so the whole fraction goes to 0. So the limit is 0. And when the limit is 0, for continuous variable x, can we say, yeah, because from the continuous version, we can jump to discrete version immediately. We can jump to discrete version immediately. Why? Remember last time I mentioned the definition, based on the definition of the limit. When x approaches to infinity, it can take arbitrary way to infinity, right? Yeah. Arbitrary way to infinity. So we make x take a special way, the discrete consecutive integer way, 1, 2, 3, and to infinity. Okay? To infinity. Goes to infinity. Because we know infinity is not a number. No. So it's a trend, right? It's a trend. It's not a number. So goes to infinity. Yeah. In this case, we get that. Log of n over n, the limit equals 0. Okay? Yeah. So this tells us little o. Now, log of n belongs to little of n. Yeah. So we complete this example. Okay. So now you know. Yeah. Now you know. Log function grows much slower than linear function. N is a linear function. Okay? Log function grows much slower. Linear function, compared with log function, it grows much faster. From this example. Okay, all right. Next one. So this time, power function, n to the d. Yeah. And here, this d, we put some condition on this d. So what is the d? D, we make it greater or equal to 1. Later we will do the discussion on this d. Yeah. And we consider the integer for convenience. Okay? Yeah. Later we will remove this assumption. Yeah. At the beginning, we consider d as a positive integer because it's easier to do the calculation. Yeah. Later we will remove. We will make a weaker restriction. Yeah. Yeah. The first time we use positive integer d. And we say n to the d belongs to little of exponential function a to the n with a greater than 1. The base number is greater than 1. Yeah. All right. How to show that? L'Hopital's rule. L'Hopital's rule. But when you apply L'Hopital's rule, you need to switch to the continuous variable version. Okay? Not a discrete variable version. Continuous variable version. And this continuous variable version, you can see it's infinity over infinity indeterminate form. So we can apply L'Hopital's rule. Take a derivative. Okay? Yeah. Then we take the derivative. The derivative of power function d times x to the d minus 1. That's the derivative formula. Okay? So here, we use the derivative of a power function formula. D times x to the d minus 1. The derivative. Okay. Denominator, yeah, we did that before. Natural log of a, parenthesis, times original power function a to the x. Okay? Yeah. But after the first round, L'Hopital's rule, this one still, we cannot see what's its limit. How to see its limit? The first round. Yeah. Because it is still infinity over infinity indeterminate form. Infinity over infinity. That means we need to apply the second round. We can still apply L'Hopital's law the second round. Okay? So the second round, derivative of power function, derivative numerator, so we get this expression. For this expression, if d greater than 2, it's still indeterminate form. We need to apply L'Hopital's law. All the way down to some point, yeah, we need to apply. If it's an indeterminate form, we keep applying L'Hopital's law. Okay? Again and again. Yeah. Until we hit this point, d factorial times x to the d minus d. D minus d 0, it's a 1. This time, it's not indeterminate form because the numerator is a constant, d factorial. It's not a indeterminate. Okay? Yeah. Then we can get a limit. Yeah. When we here, we can get limit. numerator constant, denominator exponential function goes to infinity, so its limit equals 0. So we get, so this limit equals 0, but it with the continuous variable version 0, continuous variable 0, yeah, we can jump to discrete variable version, so we get a little o. We get a little o. Okay? Yeah. All right. Yeah. So let's stop right here. Next time we will complete the remaining questions. Yeah. Remaining a few questions. Yeah. These few questions important because there are a few homework questions related to these results. You need to apply these results. Otherwise, not easy. Not easy. Okay? All right. Yeah, that's it.